Probably not, because I'm really nice. Yeah. I'm not worried about it.
So in a couple weeks, you guys are gonna show up to lab, and we're gonna be doing a lab called acid, rain, and Lewis structures. Not for a week or so, but we're gonna introduce the concept of Lewis structures now, and we're actually gonna go a little bit further than just Lewis structures. We're gonna move from Lewis structures into the shapes of molecules. So. Take a look up here real quick. This is the set of rules that you're going to see when you open up your lab notebook and you start trying to create these structures of molecules. First rule says add up the valence electrons for each atom in a molecule to get the total number of valence electrons. Second rule says place the least electronegative atom in the center and all of the other atoms around it, except for hydrogen. Third rule says draw single bonds between the central atoms and the atoms around it, counting that each bond is 2 electrons. Fourth rule, place all the remaining electrons as lone pairs on the non-central atom. Fifth rule says check that the central atom has an octet of electrons. If it does, you're done with the central, or you're done with the Lewis structure. If not, you're going to move non-bonding pairs of electrons from peripheral atoms in towards the central atom. What does this mean, and why are we doing it? That is what I'm going to try to answer right now. So, in Lewis structures, what we're doing is we're building a rough estimate of the electron distribution in a molecule. And as with other estimates that we've made, for instance, the estimates we made with oxidation numbers, our estimate is not necessarily the truth, but it's not necessarily the true electronic structure of the molecule, but if we obey these rules, we can get close to the true electronic structure. And there's a reason that these rules are written as they are written, and we'll try to explain that in brief, and then we'll try to practice using these rules. Once we've built our molecules, we're going to know a little bit about the three-dimensionality of the system, and that's going to teach us about molecular shapes. So the first rule, add up all your valence electrons for each atom in a molecule to get the total number of valence electrons. The reason that we have this rule is because in bonding, we've talked about the difference between core electrons and valence electrons. The valence electrons are kind of further out from the nucleus. They're not bound as tightly. The core electrons are in those closed subshells that are packed in really tight towards the nucleus. And so core electrons aren't generally involved in bond formation with other atoms. The valence electrons, which are more available for bonding, are the electrons that are relevant when we want to start constructing molecules out of different atoms. And so the first rule says, count how many valence electrons you have, because once you build your molecule, it's going to be those valence electrons that are distributed around all of the different atoms in the molecule. So we want to know how many valence electrons we have total, because those are the electrons that are going to be shared amongst the atoms. That's the explanation of rule number 1. Now, getting into rule number 2, we're starting to try to guess what the shape of the structure is going to be. Rule number 2 doesn't always work, but it sometimes works. It says place the least electronegative atom in the center and all of the other atoms around it. In any given molecule that you're going to build, you're going to have atoms of differing electronegativities. in general, the atom that is least electronegative is going to be the atom that the other atoms surround as they try to steal valence electrons. Right? The least electronegative atom is going to be the weakest player, and so all of the other atoms are going to kind of go after it when they look to gain the extra electrons that they want to have. Doesn't always work. You can't take an atom like hydrogen and stick it in the center of a molecule because hydrogen only forms one bond. If you're going to put the least electronegative atom in the center of a molecule, it's got to be an atom that has the ability to give up, more than a single electron. And that's why in rule number 2, well, it should say, it says except hydrogen, never put hydrogen. You exclude hydrogen from that idea of sticking the least electronegative atom in the center. The atoms that surround it are going to be the more electronegative atoms, and they're going to kind of surround this central atom in three-dimensional space. Bonds are going to form. So rule number 2, you'll see there, they're using the example of HCO. They've stuck the C in the center because C is less electronegative than oxygen, right? And in this case, they put the hydrogen on the perimeter, again, because those hydrogens are, even though they're the most electronegative atom out of that group, they're not capable of forming more than one bond. So up there, they've taken that carbon, stuck it in the center. Next thing that you're going to do is you're going to start giving away valence electrons. And there's kind of a list of priorities in distribution of these electrons. First priority is that you show bonds between all of the atoms in a molecule. Molecules are held together by bonds between the atoms, and so some number of those valence electrons, the total number of valence electrons available for bonding, are going to actually be involved in bonds between atoms. So in rule number 3, drawing that single bond, just essentially proportions electrons or gives away electrons under the assumption that they're in fact going to be involved in bonds. After you do that, you're going to have a few electrons left over. Those electrons will be distributed using the priority that the most electronegative atoms get their electrons first. So in this CH2O molecule that they're building up here, we had 12 total valence electrons, right? 1 oxygen with 6. We had a carbon with 4 and 2 hydrogens. So we've got 12 valence electrons total. Once we've drawn in those 3 bonds, so the bond that connects the carbon and the oxygen and the 2 bonds that connect the carbon and the hydrogens, we've spent 6 of those electrons. Each covalent bond is 2 electrons, so you draw 3 covalent bonds. That means that 6 electrons are spent. We now have 6 additional valence electrons that we have to account for, and we're going to give them to the most electronegative peripheral atom first. Once that guy's got all of its electrons, if we still have electrons left over, we're going to go give those electrons to other atoms. The reason that we give the electrons to the surrounding atoms first is because they are the most electronegative if we've followed the policy of sticking the least electronegative atom in the center. And so we give those electrons away to those more electronegative atoms until they're electrically satisfied. At that point, we're going to check to see if the central atom is electrically satisfied. So we had 6 electrons remaining in this CH2O molecule here in step number 3. In step number 4, we gave those electrons to oxygen, all 6 of them. At the point that we've given off or given away those 6 electrons to oxygen, oxygen is electrically satisfied. I guess I skipped this part. In terms of being electrically satisfied, what we're talking about is having filled valence shells. So if we look up here, at our periodic table, we know that oxygen tends to gain 2 electrons until it has 8 electrons in its valence. Your nitrogen, your carbon, these guys are going to nitrogen's going to gain 3 electrons until it's got its filled valence shell. Carbon will want 4. We make the approximation in the assignment of Lewis structures that that we're only dealing, at least in this class, with atoms that tend to have a filled valence shell once they've got 8 electrons surrounding them. So we're going to be looking to see that these atoms have a quote-unquote octet in their structure, except for hydrogen, which only needs 2 electrons in its valence to have a filled shell. So back to the idea that we're checking to see if they're electrically satisfied. Counting electrons and looking at this structure right here. When we're counting to determine if a shell is filled, a valence shell is filled, we're going to count all lone pair electrons as belonging entirely to the atom. And we're going to count all bonded pair electrons as counting towards that atom's filled valence shell. Now this differs from something else that we're going to do in a second. And in a second we'll do something called a formal charge analysis, where we don't count all of the electrons towards the formal charge. But in terms of counting valence shells, both non-bonding lone pair electrons and bonding electrons are counted towards that atom having a filled valence shell. So looking up here at this structure again, our oxygen atom has 6 lone pair electrons, and it feels like it has those 2 electrons in that one covalent bond for a total of 8 valence electrons. We would say that our job is complete in having satisfied oxygen's electrical requirements. The 2 hydrogens, they've got a filled valence shell if they've got 2 electrons. Each of those guys is involved in a single bond, and if they feel like they've got both of those electrons from that single bond, then both of those hydrogens are electrically satisfied. Your carbon atom, on the other hand, in this structure that we've drawn right here, does not have an octet of electrons. It doesn't have 8 electrons in its valence shell. It's got 3 single bonds, 3 covalent bonds, counting 2 electrons apiece. And so as we've drawn it here, it looks like that carbon has 6 electrons in its valence shell. Well, that brings us to point number 5. After we've checked that all the peripheral atoms have their filled valences, we're going to check the central atom. And if the central atom does not appear to have a filled valence shell, we're going to move lone pair electrons from peripheral atoms into bonding positions with the central atom. What that does, moving that lone pair into a bonding position, makes it so that those 2 electrons can still go towards oxygen's valence, but also they get counted towards carbon's valence as well. So you see here there's a little arrow. They take those 2 electrons and they create a double bond between carbon and oxygen. Now, if you go in and count to see who's got filled valence shells, your oxygen still has 8 electrons in its valence shell. And we're counting valence, it's got 2 lone pairs, plus there's 2 bonds, and both of those electrons, or both of the 2 electrons in each bond counts to the valence. So oxygen looks like it's got 8 electrons. Your carbon now, in this structure, has 8 electrons in its valence shell. 2 bonds to hydrogen, 2 electrons apiece, and now a double bond, 2 bonding pairs of electrons to the oxygen for a total of 8. Go ahead.
So are all elements satisfied by 8 valence electrons besides hydrogen?
All of the ones that we're going to give you for this. Once you get expanded volumes around atoms, they don't always obey the quote-unquote octet rule. Some have quote-unquote expanded valence shells, but for the first 2 rows of the periodic table, it's safe to assume that they act to have a filled valence shell. Once you get into the 3rd row, some of those atoms behave differently.
Okay.
But we'll give
hydrogen is the only reduced one you're going to deal with.
hydrogen is the only one that requires simply 2 electrons.
Okay.
All the other problems that we're going to give you in this class are going to be atom types that are electrically satisfied when they've got 8 electrons in their valence. So that part's going to be easy. What I want you guys to remember about this Oh, wait. So backing up for a second. So this structure right here that we've shown with the central carbon and the surrounding oxygens and hydrogens, all of those atoms have enough electrons to satisfy their valence requirements, right? And so at this point, we would stop and we would say, this is a good structure. Now here's the story. This is an approximation. A lot of the stuff that you're learning in Gen Chem is an approximation. It's not necessarily true that there's exactly 2 electrons located between this carbon and this hydrogen, or that there's exactly 4 electrons located between that oxygen and that carbon. But this is a good structure. It's one of the best structures that we can come up with based on just using this sharing of valence electrons requirements and the concept that we have to have single bonds containing 2 electrons between each atom. Once we have a Lewis structure for an atom, we can know something about molecular shapes. And here's why. Negative things repel each other. Anytime you've got something that's negatively charged, it's going to repel something else that's negatively charged. And just accounting for repulsions between negatively charged species, we can develop a geometric shape for the molecule. Looking at your molecule here, the carbon with the 2 hydrogens and the oxygen, you've got a central carbon, and it's bound to an oxygen, and it's bound to 2 hydrogens. Now, each of these bonds contains electrons, which are negatively charged. They're all going to repel each other. And in general, they're going to move to positions that maximize the separation distance from each other because the negative charges want to get away from one another. When you have only 3 objects that are moving to positions in space that maximize their separation distance, 3 surrounding objects, the geometric arrangement that maximizes separation distance is a triangle, but we're going to call it a trigonal planar geometry. What that means is that these atoms, the 2 hydrogens and the oxygens, have moved to the vertices of a triangle relative to the central atom. You can imagine a triangle sitting here with equal angles. And so the molecule exists in a plane. In this case, we used bonding electrons. We had a situation where we had all bonding electrons between atoms. Sometimes you'll see non-bonding electrons. Non-bonding electrons also repel other negatively charged things, and so if we're looking at shapes of molecules, we also have to consider those non-bonding electrons. Here's an example of that. In a water molecule, we've got a central oxygen. It's bound to 2 hydrogens. If you put the Lewis structure together, you'll end up finding out that you got a couple of lone pairs sitting on those oxygens. Well, these lone pairs, they don't exactly sit right on top of the oxygen. They occupy a whole space above that, or projecting outside of that oxygen atom. So these electrons occupy space, these electrons occupy space, this single bond occupies space, and so does this. Because they're all negatively charged, they all repel each other. So this molecule has 4 objects surrounding a central atom, and they all move to positions in space to maximize their separation distance. This will end up looking like a tetrahedron surrounding, I don't even know how to draw a tetrahedron. Take 4, okay, this will be easier than drawing it. That's how I used to do it. Take 4 objects surrounding a central atom in space and move them to positions that maximize their separation distance, and you get that guy, right? This is called a tetrahedral geometry. central atom here, and all of these guys pointing to the vertices of the tetrahedron. You notice that if I turn that upside down, there's a triangle down here, a peak up there, just like in the tetrahedron. And that's the short of it. Or in short, that's what we do. You're counting valence electrons, and you're giving them away to all of the different atoms involved in bonds in the molecule. You're checking to make sure that every atom is electrically satisfied based on the assumption that it needs 8 electrons in its valence shell, unless it's hydrogen, it needs 2. And you're building these structures. You're going to do something called a formal charge analysis. I'll talk about that in a second. And once all of those things are done, you're going to present a structure for this molecule that is your best guess of how the electron density in that molecule is distributed. Okay? Again, it's just an approximation. It's not a true electron density, but it's close. And oftentimes it's close enough to be very useful for predicting the behavior of these molecules. We're going to be doing a lot of this. We'll just do some practice today. One more thing that I need to talk about, and I'll talk about it in the context of a problem. So let's build a CO3 2-. How many valence electrons do we have? There's 3 oxygens in there, plus a carbon. But the species is not neutral. It's got a 2 negative charge. And so it's got an extra 2 electrons in addition to the electrons from the carbon and the oxygen. So we've got 1 carbon, and that has 4 valence electrons. We've got 3 oxygens, and that's 3 times 6 valence electrons for 18, right? But we have a 2- charge. So that's 2 times 1 minus another 2 electrons. So if my count is correct, there are 24 electrons available for bonding in the CO3 2- ion. Yeah? So, first thing we do, count electrons. The next thing we do, rule number 2 that was up there a second ago before my computer turned off, is to place the least electronegative atom in the center. So we're going to take this carbon, this least electronegative, we'll stay in the center. Now, that atom is going to be attacked by all of the other atoms as they look to gain electrons to fill their valence shells. And so we'll stick these oxygens in surrounding positions around that carbon. Now, we're going to assume that this molecule is held together by bonds. Draw covalent bonds, each representing 2 electrons, connecting all the peripheral atoms to the central atom. And we're going to watch on our count as we spend these electrons. So we had 24 electrons to spend, but we just consumed 2, 4, 6 in the form of single bonds to the central atom. We subtract that 6, we've got 18 electrons left to spend. Okay? Again, the rule, I think it's number 4, place remaining electrons as lone pairs to the surrounding atoms. We do this because the surrounding atoms are more electronegative, and so they get priority on electrons. And give the oxygens these electrons until oxygen shows a total of 8 electrons in its valence. That means that each of these oxygens is going to require 2 lone pairs, or sorry, 6 lone pairs. 3 lone pairs, 6 electrons, something. So we get 3 lone pairs around each oxygen. That's 6 electrons apiece. 6 times 3 is 18. We're going to subtract from the remainder of electrons the 18 that we have left. We now spent all of our valence electrons. They're all distributed around the molecule. All of our oxygens have their valence shells filled. are electrically satisfied, but your carbon is not electrically satisfied. In that structure that we've just drawn right there, that carbon has only 6 electrons in its valence shell. We want 8. And so we're going to obey rule number 5 and start moving lone pair electrons on the peripheral atoms towards the center as bonding electrons. We do this one time, and carbon will have its octet satisfied. So take those 2 electrons, get rid of them, move them into a bonding position. Now we've got this oxygen still has 8 electrons in its valence. This central carbon with 4 covalent bonds surrounding it has 8 electrons in its valence. Yes?
For what you just did, like rule number 5, does it matter for which atom you do it with?
In this case, no.
Like for others, if they have different
Yeah,
atoms?
for others it will, and that's gonna be elucidated by something called a formal charge analysis. So what I didn't do on the last example is I didn't analyze formal charge. And here's what formal charge analysis does. In formal charge analysis, you count how many electrons you're showing the atom associated with in your Lewis structure, and you're comparing that number of electrons to the number of electrons that the atom normally comes with. Okay? And you'll take the difference of those numbers, and the difference of those numbers will be something that you, a number that you assign to the atom called its formal charge. So let's do this with this molecule here for a second. So, oxygen. We'll do this oxygen right here. Normally comes with 6 valence electrons. Oh, this is the other part I had to tell you. So for formal charge analysis, each atom gets credited with having all of those electrons in lone pairs, but we only count half of the bonding electrons towards that atom. So this is kind of weird. We've made a few different approximations in assignment of different charges to species. When we did oxidation numbers, we took shared electrons, and we decided that whichever atom was most electronegative was going to get credited with both of those electrons. That was an approximation. It's not necessarily true that in a given bond that both electrons move to the most electronegative atom, but it was an approximation that was useful for our purposes. We're going to use another approximation, and that is that in these Lewis structures, the bonding electrons are split evenly. So when you see a single bond between 2 atoms, you're going to count in terms of formal charge analysis, 1 electron towards one atom and the other electron towards the other. So getting back to this structure, oxygen normally shows up with 6 valence electrons. Yeah? 6 in the neutral. Oxygen. You're going to subtract from the number in the neutral atom the number in your Lewis structure. Well, in your Lewis structure, you're going to count all of these lone pairs towards the oxygen. But again, you're going to only count half of the bonding pairs towards the oxygen. So if you do a count for this oxygen, it's got 2, 4, 6 plus 1 is 7 electrons. And so according to formal charge analysis, this oxygen atom is associated with 7 electrons. So we take the number of electrons in the neutral atom, subtract from it the number of electrons we show in the Lewis structure, and the number that we get is our quote-unquote formal charge. So we would say that this oxygen has a -1 formal charge. This oxygen right here, this guy has an identical structure to that one, so we can say that this oxygen also has a -1 formal charge. This oxygen up here, again, oxygen normally comes with 6 electrons. We've got 2 4 electrons in the form of lone pairs, and then plus half of 4 bonding electrons. So 1 electron from that bond, 1 electron from that bond, is 6 total electrons that we're showing this oxygen associated with. And so its formal charge is going to be calculated this: 6 electrons in the neutral atom. We're showing it with 6 electrons in our Lewis structure. So we're going to give this guy a 0 formal charge. That guy was -1.